So, Assalamualaikum, and today our group will present about the insect classification via image processing by using bee and butterfly classification. So, without wasting our time, let's go to the next page. So, this is our group members, led by Ahmad Wafi bin Khalid. Second is me, Muhammad Naufal bin Ismail, Muhammad Afiq Izzat bin Muhammad Zaidi, Naufal Hakimi bin Rosmi Azwa, and lastly, Muhammad Nur Harith Shafiq bin Muhammad Nasir. So, let's go to the main parts. So, for the workflow pipeline. So, for this project, firstly, we use the converse input from RGB to HSV by select saturation channel. Second, we do the filter and segmentation by using Gaussian blur, noise reduction, and also adaptive thresholding. Third, we use a refine by morphological opening, closing, area-based code filling. Fourth, we use the features, extract 5 shapes and 3 colors numerical features. And last step is using KNN, K equal to 3, Z-score normalization followed by manual KNN voting. So that's for the workflow. So move with the next presenter.
So first of all is our project overview. So this project propose and implement a traditional NetNet pipeline where we classify bee and also butterflies. So the system will process the image via 4 different types of process, which is HSV conversion, Gaussian filtering, Oxford thresholding, along with morphological refinement. So after each of the feature being extracted, uh, manual KNN classifier will categorize the insect with performance evaluated using a confusion matrix, accuracy, precision, and recall. Next, we look on how we get the dataset. So from the given dataset, there are 3 different types of insect, which is dragonfly, bee, and butterfly. So for this project, we use bee and also butterfly images. So a total of 40 images were used, where the image were divided into training and testing set. As you can see on the table, we have 10 training image of bees and also butterfly, along with 10 testing image of bee and butterfly.
Now I will explain about the pre-processing and segmentation. The first one, now I will explain about the pre-processing and segmentation. First step is RGB to HSV color space conversion. To better separate, ciao. Now I will explain about the pre-processing and segmentation. The first step is RGB to HSV color space conversion. To better separate the insects from the background, the image are converted from RGB to HSV. The saturation channel is used because it highlights color intensity, making the vibrant bees and butterflies stands out clearly from the background for easier classification. The next step is RGB to HSV color space conversion. Gaussian filter is applied to the saturation channel to smooth the image and remove fine noise. Cleaning the image before thresholding is a key step that prevents background noise from ruining the final binary mask, ensuring a much sharper and more stable segmentation result. The third step is Otsu thresholding. Otsu's thresholding automatically finds the best value to turn the image from a clean black and white mask. It separates the foreground from the background, turning the inside region white and the background is black. The fourth step is morphological refinement. To clean up the messy initial mask, morphological closing fills the tiny gaps inside the insect's body and wings, while opening remove stray background noises. This operation smooths the edges and create a solid, accurate outline of the insect for feature extraction. And the last step is final segmented insect region. The final binary mask is applied to the original RGB mask. Pixels outside the detected insect mask are set to black, while the detected insect region remains in its original color. This produces the final segmented insect image.
So now we are going to have a look at the feature extraction that we are using in this project. So there are 2 features that are being considered, which is shape features and also color features. So shape features are being extracted from the final binary mask of the insect. So these features describe the size and also the structure of the detected insect. So the shape features included area, where the number of white pixels in the final insect mask, perimeter, which is a boundary length of the insect region. Circularity is when how close the detected object is to a certain circle. And then we have also aspect ratio, where the features compare the longer side and the shorter sides of the insect. And last but not least, eccentricity, where it's show how elongated the object is. And next is color features. So color features are being extracted from the original RGB image, and only pixels inside the final insect mask are used. So in color features, we have to consider 3 types, which is mean red, mean green, and also mean blue. So mean red is average red value inside the mask, and then we also have mean green, which is average green value inside the insect mask. And last but not least is mean blue, where the average blue value inside the insect mask.
For the classification design, we use the K353 It's ideal for the small dataset, simple, highly interpretable, and perfect for comparing numerical feature vectors with 20 training image. Second, voting mechanism. The classifier evaluates the three nearest training points and determines the class P versus butterfly via majority votes. So we use manual canon implementation. Toolbox independence developed manually from scratch in MATLAB because the built-in function requires the statistic and machine learning toolbox. So this is your step. Extract features, normalize values, calculate distance, apply k equals to 3 majority votes. This is step-by-step workflow. Training and testing feature are extracted, normalized, mathematically compared via distance, and classified without relying on internal toolbox function. So next, feature normalization and vector comparison. Then state of normalization, eliminating scale bias, extract features very drastically in scale. Preventing dominance, normalization prevents large-scale features from dominating the distance calculation, ensuring all the features contribute equally. So this is the normalization formula. And that's how image are compared. Features, vectors, not sorry. The system compare abstract feature vectors, not the original image. So this is how they are compared features. So lastly, the distance principle. A small distance indicate high feature similarity, while a large distance indicates different features. So
So Assalamualaikum warahmatullahi wabarakatuh and welcome everyone. Today I will be walking you through the quantitative evaluation of train KNN classifier. To evaluate the model's performance, we use testing set of 20 unseen image which were evenly split by 10 bees image and 10 butterfly image. Each of the testing image was processed using our standard image processing pipeline. As you can see on the right side of the slide, you can see the table of raw classification results where we compare to the actual label of each image against the label predicted by our model. So moving on the next slide, we have the confusion matrix which provides a clearer visual breakdown of our results. Looking at the top row of the actual bee image, you can see that 9 images were correctly predicted as bees, while 1 bee image was wrongly predicted as a butterfly. In the bottom row, for the butterfly image, 8 were correctly predicted as a butterfly, while 2 were incorrectly predicted as a bees. So finally, let's look at this number mean of our overall performance matrix. Our overall accuracy, which is percentage of all image that model guessed correctly, was 85%. That show is a 17 out of 20 that predicted correctly. Next, we look at the precision, which tells us the percentage of true positive out of everything the model claimed was a certain insect. We achieved precision of 81.82% for bees and 88.889% for butterflies. Then we have a recall, which is a percentage of actual image of certain insect that the model successfully found. Our recall was 90% for bees and 80% for butterflies. Averaging this out gives a solid macro precision of 85.35% and macro recall of 85%, demonstrating that the classifier has a very balanced and reliable performance across both categories. Thank you. So for the error analysis and discussions, finally, let's look at our errors. Our system achieved 85% accuracy, correctly guessing 70 out of 20 image. So we look into the 3 mistakes and found the 3 main causes. First, background noise. Because the image weren't cropped, part of the background accidentally got mixed in with the insect data. Second, segmentation limits. Small insect or one that blended into their surroundings were hard for our system to separate the background. And lastly, mass deformity. Because of the first 2 issues, the system sometimes created incomplete shapes that didn't accurately match the real insect. Understanding these 3 errors tell us exactly what we need to fix and improve the models next time. Thank you for listening.
So, as a conclusions for the proposed system, the traditional pipeline successfully developed a bee and butterfly classification system in MATLAB using fundamental image processing without image cropping. Second, robust segmentation converts RGB image to HSV space, extracting the saturation channel and applying Gaussian filtering, also thresholding, and morphological refinement to create the insect mask. And last, features extraction, evaluate 8-dimension feature vector containing shape features and color features. Second category, key finding and performance, classification accuracy, the manual can end, k equals to 3, classifier achieved 85% accuracy rate, correctly classifying 17 out of 20 unseen testing image. And for the limitation analysis, system performance was occasionally degraded by complex background variations, small insect size, and segmentation boundary errors. So lastly, for the future enhancements, texture features integrate reliable co-occurrence matrix, GLCM, for texture extraction, robust segmentation, improve thresholding methods to handle noisy or highly textured background, and lastly, hyperparameter tuning, test various k values, and significantly expand the training dataset size. So that's all from us. Thank you.